Well, hello everyone, and welcome to Talk Nerdy. Today is Monday, August 2nd, 2021, and I'm the host of the show, Cara Santa Maria. And before we dive into this week's episode, I do want to thank those of you who pledge your support to make Talk Nerdy possible each and every week. Remember, I will never charge for you to listen to the show. The show is 100% free. And, even if you are a patron, are not a patron, it's always going to be free to download. What my patron account really is about is for individuals to show their support, to be able to help offset the cost for people who wouldn't otherwise be able to afford to listen, in case if I had to put it behind a paywall or charge a fee, which of course you've got to do in an effort to actually get paid as somebody who makes a thing. And yes, I sell ads on the show, and that helps offset a lot of the costs. But with the numbers that the download counts that we have, advertising really doesn't cover it. It doesn't cover a decent paycheck for me. It definitely doesn't cover me being able to pay my assistant and pay the editing service that I use. So because of that, I really do rely on support from people just like you. This week, the people just like you include Mary Neva, Rob Schreck, Pasquale Gelati, Brian Holden, Christopher Pitts, Daniel Lang, David J.E. Smith, Dudas Infinitus, June Sapara, Ulrika Hagman, and Robert Chris. Thank you all so very much. And so let's dive right in. We've got a great show for you today. I had the opportunity to sit down with Dr. Grace Lindsay. Now, she's the author of the book Models of the Mind: How Physics, Engineering, and Mathematics Have Shaped Our Understanding of the Brain. She's actually a computational neuroscientist who's based at University College London. She studied and finished her PhD at the Center for Theoretical Neuroscience at Columbia, and she focused her research on building mathematical models of how the brain controls sensory processing. She was also awarded a Google PhD fellowship in computational neuroscience in 2016, and of course speaks all over the world on the topic. So without any further ado, here she is, Dr. Grace Lindsay. Grace, thank you so much for joining me today.
Thanks for having me.
Yeah, so we're going to be talking about your new book, Models of the Mind: How Physics, Engineering, and Mathematics Have Shaped Our Understanding of the Brain. And this book, I mean, correct me if I'm wrong, but this is the book for what you do, right? Like, this is the book that communicates the work that you do.
I hope so, yeah. That was cool. The intent.
And is this your first book?
Yes.
Yay! Oh my gosh. Well, first of all, congratulations.
Thank you.
I've not yet written a book by myself, and the feat feels daunting and overwhelming. So anybody who does it, especially if they are is it safe to say somewhat early career?
Yeah, by the standards of academia, I am early career.
Yeah, I mean, then that's like just a massive accomplishment. I see that when did you actually finish your PhD?
It was the end of 2017.
Yeah. Okay, very cool. And then a Google PhD fellowship in computational neuroscience in 2016. Oh my gosh. Okay, I'm so excited to talk about your background and to talk about a lot of the stuff that you dive into in the book. So just real quick for everybody, I've said it already in the intro, but I'll say it again. The book is Models of the Mind: How Physics, Engineering, and Mathematics Have Shaped Our Understanding of the Brain. So that my background is neuroscience, not at the level of yours. I stopped at the master's level and then switched back gears over to psychology. And I was doing a lot of network neuroscience. So it was, for me, a lot of biology with a bit of physics. And once we got heavy into the computational stuff, I was like very heavily relying on my colleagues because it was a lot. And I'm very excited to, first of all, I guess maybe carve out, before we even get into your background, the field as a whole, because I think a lot of people don't realize how multifaceted neuroscience as a word is. Oftentimes, have you ever had this experience? You're like in a bar, maybe not a bar. I'm like, do people go out in public anymore? Back in the day, you're out in public and somebody goes, "What do you do?" And you go, "I'm a neuroscientist." And they go, "Oh, so you do brain surgery?"
Yeah, that sometimes people mishear and think I said nursing.
Oh, right. Yeah. So there's, neurobrain, science, pretty broad term, neuroscience, and it encompasses a lot, doesn't it?
Yeah. yeah, neuroscience itself, even not thinking yet about computational neuroscience, is super interdisciplinary. It's chemistry, it's biology, it's psychology. It's the attempt to connect all of those things. So there's people working across those levels and disciplines. It involves understanding of optics to, use microscopes and electricity and physics and things to build other tools that we use to record from the brain. So it's got a lot going on, just basic neuroscience itself. And then the computational mathematical side has even more thrown into it.
Absolutely. And so before you got to your PhD, when you were coming up through bachelor's, maybe even master's, some people go straight after bachelor's, some people get a master's along the way. Did you come up through biology, through chemistry, through physics, through mathematics? Kind of what was your academic path to get you to computational neuroscience?
Yeah, so when I was in high school, I knew I was interested in the brain, and I learned a little bit about psychology, but I thought, well, I want to know like how the brain does psychology, like what is the actual physical things that underlie the mind and what we study in psychology. And I didn't know what the word for that was. I didn't know that neuroscience was the word for that. And I thought it was like biological psychology or something like that. But I eventually found neuroscience, and I decided to get my undergraduate degree in neuroscience at the University of Pittsburgh, which, I don't know how common it is now, but certainly the further you go back 10, 20 years, the less common it is for undergraduate programs to have majors in neuroscience. So it actually took some fishing around to find a school that had a fully dedicated neuroscience program.
Oh, for sure. My master's is actually, I say it's in neuroscience, but it's in biology. It's just I only took neuroscience courses. So sometimes I'll say neurobiology, but my school just didn't offer a neuroscience degree. So I have a master's in biology, but everything I did was neuroscience. And I think that's common. For a lot of people who, I got my master's in 2007. So around that era, I think that's pretty common.
And I graduated undergrad in 2011. And I think that also speaks to the interdisciplinariness of neuroscience and its almost newness as its own category, because it was just biologists studying the brain, or people interested in chemistry and biochemistry studying neurotransmitters and stuff like that. And you didn't have a cohesive department dedicated to neuroscience in most schools. So that's why That's why I wanted to go to a school that had a neuroscience program, because I wanted to get an education in kind of the full stack of the brain. But I thought that I would be doing wet lab work, experiments, maybe something related to clinical neuroscience or translational neuroscience, something useful in that direction. And that's kind of what I started out doing as an undergrad. I worked in some labs, obviously in the way that undergrads do, which is not super helpful, probably. Just picking up mice and, doing exactly what you're told and afraid that you're doing it wrong. But I got some exposure there. But while I was at the University of Pittsburgh, I discovered computational neuroscience. And ironically, when I looked for universities, I wasn't interested in any university that focused on the computational side of neuroscience. I had the mistaken belief that meant that we thought that the brain worked exactly like a modern computer. And I thought that sounded silly. The brain is its own thing. There's no reason that we have to assume it works like a computer. And so I didn't want that side. Yeah.
Like those people don't know what they're talking about. One day they'll realize.
It was like, that just seems like computer scientists trying to claim everything. But I as an undergraduate, I learned what computational neuroscience actually was, because there is a pretty good concentration of it at the University of Pittsburgh, coupled with Carnegie Mellon University, which is across the street. They have a kind of joint PhD program in neural computation. And so I was exposed to some of that while I was there. And then I decided to switch up my coursework to take more mathematics and learn computer science and computer programming so that I could start doing research in computational neuroscience, because it felt like a very satisfying way to answer the questions that I ultimately had as a high school student, thinking, I don't just want to know what the brain or what the mind does in psychology, and I don't just want to know what the brain does. I kind of want to know how and why it does it. And it felt like these mathematical models that are common in computational neuroscience, they were getting at more of a how and a why answer than just collecting data and experiments.
Yeah. And I think that's That's something that is going to be important for us to come back to time and time again, is that even though sometimes we can get in the weeds with this kind of work, and like sometimes the studies start to feel kind of wonky with regards to their results, it all comes back to this larger question, which is sort of like, how does brain become mind? What is happening in brain to lead to the more kind of subjective experience, or to lead to this more kind of this understanding that we have of mental processing, of cognition, of emotion, of sensory processing, motor processing, all the different things that the brain does. How does this happen? How does it happen at the cellular level? How does it happen at the molecular level? But also at this network and systems level. How is it that these cells, the way that they communicate with one another, do so in such a way as to create language and poetry and mathematics and self-reflection? I mean, ultimately, all of these different disciplines are still hacking away at that basic problem, aren't they?
Yeah, that certainly seems to be like, the core question that a lot of people have when they want to study the brain. And just as you described it, the scope of that problem is so big. It spans so many levels, and it's got breadth and depth as a problem to solve scientifically. And to me, that's why it's obvious that we need to use mathematical models to get a hold of that at all. I mean, there's no way that you can just kind of go around with your wordy descriptions of how you think the brain works and be able to capture all of those different sub-questions to explain how the molecules of a neuron can build up to human behavior and thought. You're not going to be able to get it all without writing it down in mathematics at some point.
Right. And so that kind of leads me to the question that I think will guide us throughout our discussion today, which is how then did you distill what you know into this book? Like it's such a big question. And it's a big question in terms of the fact that we don't have the answers. We have a lot of answers, but we definitely don't have all the answers. And there are even some whole swaths of information that we're lacking. So how did you even begin to approach talking about computational neuroscience in a way that's distilled and understandable?
Yeah, it is a scary topic to, approach a popular science publisher with or anything like that, because really kind of two common phrases like, oh, it's not brain surgery or it's not rocket science, like meant to refer to, something isn't so complicated as these two most complicated things in the world. Computational models of the brain are kind of a combination of brain surgery and rocket science. It's like,
Right.
It's the biology of the brain plus the math of physics. For the most part, a lot of it comes from physics. And so it's a daunting thing to try to tell people they will be able to understand. But at the root of it, again, are these very basic questions of like, how does memory work? How does vision work? How do we make decisions? That kind of thing. And people have an interest in understanding that. Obviously, a lot of people, not just neuroscientists, have some interest in how the brain works, how their brain works. And so I wanted to, point out the ways in which the mathematical models help us get at those very common, relatable questions about the brain. And I also took the approach of focusing on, in a kind of history of science way, the evolution of an idea about the brain over time and how it changed with interaction with mathematics. And, when physicists came in and tried to take their own spin on the problem, how that changed the way neuroscientists thought about it. Because that narrative, even if you're not understanding every biological or mathematical detail, you get the gist of what happens when we bring quantitative methods into biology. And that's really what I wanted to get across. Not that every single detail in this book is the absolute truth about how the brain works. It's an evolving thing that we're studying. And there's a lot of things we got wrong. And there's a lot of things that we just don't know at all yet. But this approach of coming at it with the intent of building a formal model of how you think something works, I think that that's a theme that you can see throughout computational neuroscience, that approach is helpful in clarifying your thoughts and clarifying your hypotheses. And I think it just makes for a very interesting story. At least for some of the chapters in the book, it wasn't that hard in my mind to make it interesting because it is just so fundamentally interesting of what happens when people cross disciplinary lines and what kind of new exciting frameworks can come out of that. That story is fun to tell for me. So I really tried to make it a narrative approach. And also, in the main text of the book, I think maybe there's, two very simple equations that you have to look at all. There's a mathematical appendix for people who want more equations, but it's about conveying how the equations are useful and how they help us clarify a lot of experimental findings.
Right, right. I like that. I think that maybe one of the things that we can do, and hopefully we can sort of toe the line. Sometimes I struggle on the show, especially with books that cover these very kind of encompassing topics. How much of what we do on the show is content and how much is process, which is a very psychology therapy way to kind of say, are we talking about the actual meat in the book, or are we talking around the meat in the book, why it matters, why it's important, what is how we came to know what we know, or are we talking about what we actually know? And I often struggle with that on the show, but I try to kind of strike a balance, even though I tend to be much more into the metacognitive stuff and the sort of I don't know, the talking about the talking. But when it comes to models of the mind and to the work that you do as a computational neuroscientist, there's probably some basic understanding, some basic knowledge that we should maybe make sure that we all agree on a shared vocabulary right now. So maybe you can give us the sort of few-minute elevator pitch about like the basic building blocks of the brain, like what's a neuron, how do chemicals work in the brain, how do these different fields contribute to what we know about how the brain works, just kind of maybe starting with the cell or the subcellular level and moving on. Do you think that that's a fair thing to ask? Like the quick and dirty?
I don't know if it's fair, but I will try.
Thank you.
Yeah. So I think starting at the neuron level is a good place to start. That's where I start in the book.
Mm-hmm.
And that's where, a lot of computational neuroscience is focused on neuron level and above. Neurons are cells that make up the brain. They're not the only cell type in the brain, but they're the ones that we focus on the most as neuroscientists. In terms of, to get right into how we use mathematics and inspiration from physics and all of that to think about the brain, it turns out that neurons conduct electricity. That's how they send signals to each other and across the neuron itself. And we can use the same equations that engineers use to describe electrical circuits using things like capacitance and resistance and all of that. We can use that mathematical framework to make a mathematical model of what a neuron does, where we can say, well, if I build the neuron to have this kind of resistance and all of that, and I give it some inputs in the form of current, it will produce some outputs. And that's the very broad strokes way that neuroscientists think about neurons. They get inputs and they produce outputs. And the large number of neurons that we have in our brain doing that all at once together in certain ways leads to what the brain can do, which is kind of everything. So simple building blocks, but they lead to more complex things. And then as you go up in scale, you get populations of neurons that interact together. The way that you connect these neurons will control how they do certain computations. A whole population of neurons, if connected in a certain way, can do computations. There's a chapter in the book about memory and how populations of neurons, if they're connected the right way, can recall a memory. So you can put in a little bit of input of something, like you got a cue that kind of reminds you of something, and then this network of neurons through its interconnections will reactivate in a way that pulls up the whole rest of the memory. And so that's what you get when you start to have populations of neurons. They can do more interesting things like that. And we have different mathematical techniques that are meant to study populations of neurons that don't require that you model each individual neuron individually. Actually, you can kind of think of the population as a whole in a different style of mathematical framework. And we can keep going up and up. And this is kind of the way that the book is organized, from the small scale up to the larger scale. And we can think about whole brain areas and how they interact and how they connect and how information can flow through the connections of different brain areas. And so that actually gets into things like network neuroscience and graph theory and mathematics that is actually used a lot of times to study social networks and other naturally occurring networks in the world. We could use that kind of mathematics to study the brain at a larger level and think about how, connections in the brain can change the functioning of the brain and kind of relate the structure of the brain to its function. And then also we can study behavior with mathematical models. So you can have experiments in the lab where you ask people to respond to certain stimuli on the screen to report what they perceive. And you can build a model that tries to, even without thinking about neurons or taking into account the structure of the brain, just tries to capture the input-output relationship that exists at the level of behavior. And ideally, what you want to do is actually go back and connect all these levels. So you have a mathematical model that just says, well, if I show a person this picture, they're going to respond this way. And that's just kind of a pure behavioral input-output model you can write down. But ideally, maybe you'd then be able to say, well, if I make a model of neurons interacting in such and such a way, it can reproduce that same behavior. And then you can now understand how the neural architecture and the function of neurons relates to the creation of behavior, the behavior that you've observed in an animal or a human. So those are kind of the scales. That's the ways that different mathematical models can come in at different levels. And each of these different types of mathematical modeling have their own history and how they were applied in other fields before they came to neuroscience. And that kind of gives some context for how they're used in neuroscience as well.
Yeah, and I want to sort of get soon to the differences between computational neuroscience, as in we're studying the brain by utilizing these mathematical models and these computational models, and neural net research, which is that we're developing sort of AI and different algorithms for computers, for machine learning based on what we know about neuroscience. And I think we'll get to that in a minute. But before we do, a question that came up for me that I just jotted down was, how much do you think computational neuroscientists focus on neurochemistry? Because it sounds like it's very heavy on neurophysics. So a lot of the electrical activity in the brain, a lot of the recruitment of different cells. If this cell fires and that cell doesn't fire, what happens? What happens when all these cells fire in succession? But how much is, neurochemicals? So we're talking neurotransmitters, the amount of chemical that's in the synapse, the things that lead to the electrical activity, or at least have some effect on the electrical activity. How much is that a part of the work that most computational neuroscientists do?
So there definitely is mathematical modeling of those subcellular processes, understanding how the neuron works as a cell, how the physics of diffusion can be important for neurotransmitter signaling. All of that kind of thing definitely does happen. And it's maybe more related to the field of computational biochemistry or computational biology, really just thinking of the neuron as a cell, a very biological thing. And thinking about it in terms of truly physics, as in just the laws of physics applied to molecules in a fluid kind of thing. Whereas, a lot of what goes under the name computational neuroscience does tend to be more at the cellular level or above, and more thinking about the computations that the brain does and almost using some physical models as an analogy more than as like literally we're modeling the physics of the neuron. So the using electrical circuits as a model of a neuron is more of a literal use of those equations. But sometimes we also take models from physics and use them as an analogy. I keep coming back to the example of memory just because it is a good one here. But in that case, we were the Hopfield network is used to understand memory in neuroscience, and it's based on the mathematics of gases and how particles interact in a gas. But if we say by analogy, neurons interact in a way somewhat similar to how particles in a gas interact, then we can still use those same equations.
Okay. Yeah. Even though it might not be a perfect kind of one-to-one match.
Yeah, it's not that we think neurons are the same as a gas.
Yeah.
It's just that there's the very abstract level, it's things interacting. And so now we can use that math in a lot of different scenarios.
And so I kind of didn't even hint to, I kind of laid out a second question, which I think I just kind of want to get out of the way at the top, which a lot of people, they think computational neuroscience, they might think the news articles that they've read and the things that they've come across about neural nets, which I hate that term. I've always struggled with the fact that computer scientists call a lot of the programming that they do around machine learning and artificial intelligence neural net programming, because it sounds a lot like neural network. Which for good reason, but it's literally not the same thing. And so do you talk much in your work about it's interesting, kind of like, what do we know about computation and mathematics, and how does that play into our understanding of sort of like neuroscience and neurobiology, versus what do we know about neuroscience, neurobiology, what's happening at the animal or human level, and how do we then apply it to machine learning and to computational algorithms of like artificial intelligence, for example?
Yeah, there's a very tight relationship there. And, in the early days of computational neuroscience and artificial intelligence, they were not super separated.
Right.
So yeah, this notion of neural networks being talked about in the artificial intelligence literature and in news articles on AI, these are artificial neural networks. They are based on how real neurons work. That was the inspiration back in the 1940s. And they have some very simple similarities. As I said, neurons are kind of thought of as things that take inputs and transform them a bit to produce outputs. And that's what an artificial neural network is made of. All these units that take in their own input, send outputs to other units. And if you connect them up in the right way, it can do pretty interesting things. So that's what an artificial neural network is. And in the second chapter in the book, the third chapter, including the introduction, I have, this whole history of this relationship, because it really is, they're so intertwined in the beginning. People were just figuring out the biochemistry of neurons and what they do. And this notion that you could use the concept of a neuron to make an intelligent, an artificial intelligence or an intelligent computer, not only is that revolutionary in the sense of like, oh, we could make machines that are intelligent. I mean, that's important and people have wanted to do that for a long time, but it just kind of added to the belief that you could actually do that. It was also somewhat revolutionary in terms of thinking about the brain as the physical thing that produced human behavior and intelligence. Because, there is historically this strong distinction between kind of the brain and the mind, and, the mind being somehow separate, somehow not actually completely determined by the brain. The brain is just this physical thing of cells, and the mind is where intelligence is. But if you can say, well, actually, I can replicate intelligent behavior using a model that's based on neurons, then that kind of collapses them. And that was very important. That was an important side effect in the history of the development of artificial intelligence and artificial neural networks in particular. And it's very interesting also the continued interaction and non-interaction between the two fields. They kind of go in and out of being in sync with each other. We happen to be in a phase right now where they're very much intertwined. I personally do research on the brain. I am trying to understand the brain, but I use artificial neural networks. I use the same kind of artificial neural networks that are used by people who build these things for Google and Facebook and all of that to do tasks that they actually need to do in the real world. It happens to be that these networks are useful as models of the brain as well as useful as tools in the real world. And we're having kind of a lot of fun right now, these two fields interacting, seeing, what developments in artificial intelligence can help neuroscience understand the brain. And, the AI people are trying to dig into the neuroscience literature to see if there are any nuggets of inspiration they can pull out to add to their algorithms to help actually advance artificial intelligence.
And what do you say to people, or like, how do you answer the question that's posed to you with regards to complexity? Sort of like, is an artificial neural net ever going to be as sophisticated? Is it ever going to be able to function exactly in the same way? Are we anywhere close to being able to approximate the complexity or the, I don't know, resiliency is not the right word, but the kind of capability of actual wet neural networks?
Yeah, so whether we ever will be able to and whether we're close are very different questions. Conceptually, I think, yes, we can. The more and more information we gather about how the brain works, there's nothing to stop us from putting that into the form of a mathematical model and running it and seeing if it, starts behaving intelligently. So in theory, yes, we could replicate the full complexity of a human brain on a computer if we had the computational power and we had the knowledge about how the brain works. Getting that knowledge about how the brain works is the whole endeavor of neuroscience, so it's rather difficult. But today, it's still pretty abstract, the relationship, and the struggle or, the tension, even in this time when neuroscience and AI are pretty close, is that they do have different goals. So AI people want to make a system that works better on the computers that they have with the data that they have for the tasks that they're trying to solve. People on the neuroscience side want to understand the brain. So there isn't actually the incentive of the AI people to completely replicate the brain in every detail because they don't need every detail, presumably, to get something that works. And also they may be able to find ways that work that are not like the brain, but to them, that's fine. It worked. So the goals are a little bit different. And also people sometimes measure, how close are our artificial neural networks to the brain. They kind of think about it in terms of how many neurons are in each. The human brain has 80 to 100 billion neurons. And the current artificial neural networks have a lot of neurons in them, but not quite that many. And that is a metric you can use, but this notion of the neuron as just this simple input-output device is a highly simplified model of a neuron. And in reality, these neurons do have all this subcellular complexity. There's shapes to the neurons that impact how they function. They use different molecules and transmitters and all these things. And so a good portion of the complexity of the brain is going to actually come from diving deeper into individual neurons and thinking of them as more complex devices than we currently do in artificial neural networks. And so it's not just the sheer size of the model in terms of number of neurons, it's also how complex is the neuron unit itself. We kind of have to go both ways before we're going to get to the complexity of the human brain.
Right. So not only are we not there, we're by certain metrics kind of not close to being there, but I'm wondering from your perspective, do you feel that there's anything black boxy about the brain? Is there anything fundamentally unknowable? Is there a reason? Is there a gestalt to it that by definition cannot be unlocked? Or do you think it's just a function of needing to continue the work, continue to refine the tools, continuing to improve our resolution? Because one day we could potentially have the ability to know what there is to know about how the brain works and replicate it.
Yeah, I think that it is knowable. If we keep going, we'll keep seeing how neurons interact and how their activity relates to intelligent behavior. It's hard and it's still a long way off, but I can't imagine any reason why it wouldn't be possible. There's a little wonkiness around consciousness and
it's kind of the big problem there.
Right. Yeah. But setting that aside, and another issue there is people conflate consciousness with a lot of other things like emotion and sometimes intelligence and things like that. I think we could, create, sometimes they're called like philosophical zombies, like a thing that from your perspective looks and behaves exactly like a human, or maybe you could think of this as the Turing test. Like you wouldn't be able to tell that this artificial brain is not a human brain, but would it have its own subjective conscious experience? That's just that's out of reach at the moment, I think, to measure or talk about.
We were just talking about this on the other show that I work on, The Skeptic's Guide to the Universe, where we're saying, will we ever get to a point, blah, 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 blah. And the question, we kept like almost moving the goalposts on the question, and we'd have to be like, no, that's a straw man. That's not what I'm really asking. And ultimately, what we came down to, or maybe it wasn't ultimately, but one of the kind of takeaways that I got from it was, does it matter if it actually approximates, if it passes the Turing test in such a intense way that for all intents and purposes it seems human-like? You know what I mean? If it's actually not self-reflective, or if it actually doesn't have consciousness per se, and how do we even define that? But to the outside observer, it can pass. Is that not the same thing? So yeah, it was actually, there's a lot of cool philosophical questions there, but I'm wondering, do a lot of your colleagues agree with you in the computational neuroscience field that it is fundamentally knowable, we're just not there yet? Or do you ever have people within the field who take a philosophical stance that there may be something about the brain that is unknowable because we ourselves are the ones reflecting on how the brain works?
Yeah, I don't think that there certainly isn't a lot of open debate about that point.
Okay,
Now, it is
yeah.
the case that a lot of times these kind of philosophical differences just go undiscussed.
Right.
And, you have an accidental conversation with someone and you go, oh, wow, we are very different in how we think about the brain. And yet we're both studying it, using the same tools. We can cite each other's research, but there's still some, fundamental philosophical difference. It tends to maybe not matter so explicitly in the research methodology.
Oh, cool. I love that. It's like
so-
when you have a really good friend and you both like all the same things and you listen to the same music and you love going out to dinner, and then one day you realize that you were like worlds apart politically or religiously or something like that, and you're like, how did this not come up?
you just set it aside and you carry on.
That's really
so it's totally possible that that's what's happening. Although it's hard for me to imagine, thinking that there is some fundamental block there and still carrying on, because it just feels like the endeavor here is we are trying to understand how the physical nature of the brain creates intelligent behavior. And if you think that at some point that's just going to totally break down and we're not going to be able to do it, how do you know when you got to that point? Because it's already hard. It already takes a lot. If I thought that there was a point where it fundamentally broke down, I may have just decided that I already hit it and give up. So I don't.
There's almost like a motivating component of continuing to shine a light on these very dark corners. That really that is what is happening here. That there are places that are still in the darkness, and we need to shine a light. It's not that there is something fundamental about them that they are unseeable. They aren't the inside of a black hole.
And it's going to be very difficult for us with our ape brains to understand how the brain works, just because it's complicated, not because it's the brain trying to understand the brain, but it's, the brain trying to understand the universe. That's complicated too. Physics is pretty tough. So I hear. But, there isn't this, there's a question of, yes, will we be able to understand it because we do have somewhat limited intelligence? But then that, again, is kind of where the mathematical tools come in. The point of the mathematical tools is to try to help you wrangle the complexity and say, well, yeah, all of that is happening. I'm going to collapse it to this kind of simple mathematical model where I don't have to carry the burden in my head of understanding all these moving parts. They're written down in symbols on a page, and I can just kind of keep that knowledge of those relationships in these equations, and that can help me get a grasp on things that I couldn't, with my own brain alone understand.
Right. When I think about the field as a whole, when I think about the book that you wrote and the work that you're actively doing, which I want to get into, as you mentioned before, you wrote this in a kind of a very narrative way. And so in order to write a book like this, not only do you have to probably have the expertise. Usually when I talk to authors, it's like, what book did you write? Well, I wrote the book that only I could write, or I wrote the book that, I was best in a position to write. And so clearly as a computational neuroscientist, like that's where a lot of your expertise and know-how comes in. Also, solid science communication, but you also had to wear a lot of hats. You had to be almost a historian of science. You had to be able to dig into a lot of things that helped you develop a narrative. So I'm wondering, what aspects of this came easier? What aspects were difficult? Is there anything you came across as you were really putting the pedal to the metal and putting this book together that you didn't know? Like, you're like, how did I get through my whole PhD program and now deep into my work, and I just didn't know this before until I sat down to do the research that was necessary to write this book? Is there anything that sort of surprised you through that process?
Oh, sure. I mean, there's so much of it I didn't know, because I don't think in most modern science education, the history isn't so focused on. I mean, there is some broad history of physics and other fundamental fields, certain parts of biology that kind of everyone is taught as you learn science. But once you get into more niche areas, it's more about giving you the details of that niche area than it is about teaching you how they came about. So tons of stuff in the history that I didn't know about how ideas came about how people were connected. There are certain people who kind of pop up in a few different chapters, which, from the looks of the different chapters, it seems like how could they possibly have their hand in all of these different areas? But when you go far enough back, those different areas were more converged, they were more interrelated, and people were really just going out there trying to get get their hands on whatever they could and try to make sense of it with the new techniques that were available to them. So there's definitely a lot of that came up in the history. And that was, a skill that I had to learn as well in doing research for the book, which was like how to understand history, because you can read things out of context and think, oh yeah, so-and-so made this claim in this year or whatever. But if you understand maybe more of the context of how words were used and what the thought was at the time, you would think, oh wait, they weren't really saying this, now modern accepted thought. They were saying something slightly different. And so just really, appreciating history as its own field of study, the history of science as its own field of study with all of its own expertise and ways of understanding, having to dig into that and understand that a little bit on the fly as I was trying to piece together these narratives of these ideas. That was, a meta skill that I had to pick up in addition to a lot of the specific details about the different areas, because it really, computational neuroscience is a little weird because what the thing that unifies it is that we're using mathematical methods to understand the brain. But as I've described, you can apply those at any level, from neurons to behavior and everywhere in between, to all different topic areas about the mind and the brain that you want to understand. And so it's crazy in a way that we put them all together. And sometimes, at a conference, you have everything from how the shape of a neuron impacts its function up to how, people learn from getting rewards and how they process uncertainty at this psychology level.
Right.
And so it's a wide range of topic areas that you're kind of expected to know in the field. And it's only because they all use mathematical methods that it's expected, that they're of the same topic. And so I have my own area of research that I'm more knowledgeable on, of course. And then the other areas, while I definitely came across them a lot at conferences and in computational neuroscience textbooks and all of that, they really are just completely separate endeavors, totally separate questions and totally separate things that are considered answers. So that obviously takes some education to make sure that you're really representing those questions and that field of study correctly.
Right. And of course, and anybody listening right now, the hope is that they'll pick up the book, they'll read about the fundamentals, they'll learn about, the state of the field, what the directions of the field. And that, is beautifully covered in your book. But in the short amount of time that we have together, instead of kind of recapitulating all of that, what I'm interested to know right now is like, what are you working on? Like, where is your head at? What are you focusing on? What kinds of questions are you asking? And what have been some of your findings so far?
Yeah, so I studied the visual system, and I am interested in a few different aspects of how we process visual information. One of them is visual attention. So if you're looking for something, like say you lost your keys, but you know that you have like a pink fluffy keychain on them, when you're scanning your room, the neurons in your visual system will change their activity to make them pink fluffy detectors, because you know that that's what you're looking for. And so to make that pop out to you, your visual system actually changes. It changes its activity. And that will sometimes lead you to mistakenly think you found something when you haven't. You get more kind of false alarms with that. But it also works well to help you find what you're looking for. And so this is...
So it's sort of is this what underlies, or this concept is one of the things that underlie pareidolia and like, why we see faces and things all the time, because we're kind of cued to look for faces, and we tend to pay more attention to faces than to other aspects. And so we see faces in like wood and on the moon and in our grilled cheese sandwiches.
Yeah, that's probably certainly related to this idea that, we're certainly interested in faces, and faces are salient. So if there's a possibility of the face, we definitely want to notice that. One of the benefits of visual attention is that you can kind of configure it on the fly. So from 1 second, you can go to like a pink fluffy detector to a particularly strong face detector to someone who's trying to detect, your cell phone instead of your keys, something like that. You can kind of change what you're looking for and change your visual system accordingly.
Really fast.
And that's, yeah. And that's useful, obviously, useful in modern times, useful for evolutionary reasons, all of that. And so one of the questions that I've studied is, how does that work? How does the visual system change in order to make you better at at detecting the thing that you want to detect. And I actually use artificial neural networks as a model of the visual system. So there's a chapter in the book about visual processing and how it is the case that the modern algorithms that we use to, for example, do image processing, again, on Google, on Facebook, the fact that Facebook can auto tag you in a picture, that kind of thing, those applications, the type of artificial neural network that people use is called a convolutional artificial neural network, and it is inspired very loosely by how the mammalian visual system works. And so they serve this purpose of both being a useful tool in AI, but also being a good model of how the brain works. And particularly useful in the study of attention, because the whole point of attention is that it makes you better at this visual task. And you want a model that can actually perform a visual task. So you can kind of give the model a image that has a bunch of stuff in it and try to make it better at finding the thing that it's looking for. And so through that, you can try to understand how attention can make us better at finding the things we're looking for. So this is really just an example of this connection across layers. You have this model of neurons interacting, and you can connect it to this behavioral benefit of making you better at detecting stuff in your visual field. And so that's why I like using these models, because they really explicitly cross those levels.
I'm interested in like how you do the work that you do, in the sense of like, when I think of the neuroscience labs that I came up through, they were like wet labs. We were doing a lot of like work with animal cells. Sometimes you'll actually see work that's like behavior driven with whole functional animals or humans. And then of course, when I think of sort of modeling, I think of like a lot of computational work. And I don't even know if the classic sort of categories of theoretical versus experimental even makes sense in a computational neuroscience setting. But like, how, what is your lab? Is your lab a computer? Is your lab a wet lab? Is like, how do you do the work that you do?
Yeah, it's coding for the most part.
Yeah,
it's writing code. Yeah. And running simulations usually on large clusters of computers that are located remotely. So using my laptop to connect to a cluster at the university, running a bunch of simulations. And in a way, especially the simulation running, you kind of get back to a setup that's almost wet lab-like, because you run a simulation, you get some data from it. It's data about artificial neurons in your model. But from then on, you can kind of treat it like normal data. You run your analyses on it, you make your plots, you try to understand what's going on. And so, especially the type of work I do, it is kind of like artificial experiments for the most part. Some people do more analytical work where they're really trying to come up with like an elegant equation to describe something, and they don't really need supercomputers to run it on because it's a simpler mathematical thing. But in the simulation work, it is almost like dealing with artificial experiments.
Cool. And is there ever an example, or is it more that you would look to the literature of the parallel or of the modeling that happens within an actual organism? I keep saying wet, but that refers to, right, like with either within or without the organism, like actual physical biological cells and how they work, which of course can happen inside a functioning brain, or you can take them out and put them in a dish and do some cool stuff. But are there any computational neuroscientists who like model and then switch over and look at how these models play out in the organism? Or is it more usually that you're going to be like looking at the literature because other people in other fields are looking at the kind of wet function of the brain?
Yeah, so that interaction between the models and the experiments is absolutely crucial. You can't know if you've built a good model if you don't compare it to the data. And that can be data about behavior, as I said, or it can be data about neural activity, what the neurons are doing. But you definitely have to have that interaction and that iteration. It is the case that a lot of people kind of have their side. They have their role. They're either doing the experiments or they're doing the model building. And that makes a little bit of sense because it does take a lot of expertise to do either of these. And so having people who specialize in that, I think makes a lot of sense. But it is becoming more and more common for people to be educated in both. So at the very least, they can talk to each other more coherently, which has been a problem at times that, they're just not understanding each other. The experimentalists don't understand the purpose of the models or understand how to use them, or the modelers don't understand the constraints of the experiments or how to really work with the data.
Right. Like that wouldn't work, but why not? Because they would die. Like I'm telling you. Yeah. Interesting.
Yeah,
I could see those
like
kinds
that.
of fights happening a lot.
Especially when a lot of the computational people, come from a physics background or something not biology related, just certain limits on what you can physically do to an organism come up.
Yeah, without killing it. Yeah, that's funny.
So it's nice to see an emergence of people doing both, or there being kind of joint labs that work closely together where one person is more in charge of the computational side and one more in charge of the experimental side, because you do need that tight iteration and that tight understanding. As I said, we kind of pretend that computational neuroscience is this unified field because it all uses math to study the brain. But in reality, there's a lot of domain expertise with what part of the brain are you studying, what behavior are you studying. You got to know that stuff if you're going to build a good model. You can't just know the math side of it.
Oh, for sure. I mean, I can tell you that when I was working on my master's, I was towards the end of my degree, I was also like managing our lab, and we were a network neuroscience lab. We were electrophys. We were doing a lot of like MEA work with mouse tissue. So we're putting, we're taking brain cells out of the mouse, putting them on these plates. These plates had embedded electrodes, and we're measuring the activity of like big clusters of cells and doing some cool stuff with our findings. And I am published on a paper that I do not understand. Like this is like, because I contributed all the wet work to the paper. And then the computational, they were actually in the physics department, did a lot of computational neuroscience and neurophysics work it was not my field of expertise. And I can imagine that, this was my only experience in that, but I can imagine that is not uncommon. And it's cool to hear that you're saying that there are, researchers out there who are like, I want to know both. And maybe I'm not going to be amazing at both. You only have so much bandwidth, but I want to at least understand what the math is telling me, because I look at that paper and I'm like, okay, I know what I did in the methods. I know about this part of the results and this part of the intro. And then there's just whole swaths where I'm like, I don't speak that math language that they're speaking.
Yeah. Yeah. And I think your story is not uncommon, but hopefully, becoming a bit less uncommon as we do offer at least some intuition about how these things work and why you would do them and why you would choose one modeling technique over another. I'm very hopeful that word is getting out and there's kind of a more holistic understanding that's coming where everyone is agreeing that we need both sides in order to really get what we want to get done out of doing neuroscience.
Love it. Love it. Gosh, I literally could talk to you for hours about this. Clearly, this is something that I'm fascinated by. I'm still very, I think I need to keep reading in this area. It doesn't come naturally for me. I don't know if it comes naturally for anybody, honestly, but it's such important work, because I think really this is the future in many ways of neuroscience. And I thank you so much, Grace, for like putting together this very public facing book. It's not an academic book. This is a trade book. This is written for an audience that does not have background in this area. And I think it's such an important thing that you did. It could not have been easy. And I think you're really doing a service by helping communicate these issues that are, not issues, but what are their methods, understandings that are fundamental, I think, to the future of our experience on this planet, that don't need to be in a black box for kind of folks who are not neuroscientists. It's knowledge that we should be privy to as well. And I think you do a great job of communicating something that could be very daunting to a lot of people. So I thank you for that.
Thank you. That's like exactly what I was hoping the book would do. Explain something important about how we're going to understand the brain in a way that is not overwhelming or nearly as complex as people think it will be.
Right. And so, gosh, I feel like I could, again, ask you a million more questions. Before I get to my final two, I always close with the same two questions. But before I get there, is there anything from your perspective that you feel like, why didn't we talk about this? I can't believe we didn't say this. Is there anything that kind of sticks out to you?
No, I think we covered the book at a meta level pretty well. I mean, obviously, it's full of very specific details about different brain processes and histories and all of that kind of thing. But as an overview of the goals of it, I think it's pretty good.
Good. And yeah, guys, read the book. Come on, this is where you're going to get all the good stuff, all the meat. And so before we close out, I do want to, I do hope to ask you the same two questions that I ask all of my guests. I get guests from all walks of life and all different fields of science. So I'm always super interested in where their head is at with regards to these big picture questions. So are you ready for them?
Sure.
All right. So when you think about the future in whatever context is relevant to you, it could be, contextualized within your work. It could be contextualized within larger social issues, even global kind of, future of humanity, the future of the cosmos. Who knows? Number one, what is the thing that is keeping you up the most at night? The thing that you're most concerned about, pessimistic about, maybe even cynical about. But then on the flip side of that, to end on a more lighter note, I guess, or at least a more positive note, what are you genuinely hopeful for? What are you really authentically optimistic about?
So the answer to the first is climate change, and the answer to the second is the effort to fight climate change. I've been learning more and more about it. It's, I think it's a responsibility of everyone, truly everyone, to learn about climate change and learn about what needs to be done to stop it and to adapt to it, because it's not entirely stoppable. And so that is terrifying. The more you learn, you kind of go through waves of being like, oh, that's going to happen. And then like, okay, I guess that's going to happen. We're going to have to deal with it. And then you learn another thing. You're like, oh God, that's going to happen too. So it's terrifying. It's legitimately terrifying. But seeing people who truly just want to help and have the know-how and have the energy to do it, seeing them go at it and really like give it an honest try and do the hard emotional work of convincing other people that we can fight it and we have to, and just keeping spirits up about that is very, it's an amazing human thing to witness.
Yeah. No, I definitely agree. And I'm always taken aback by how salient this issue really is. I mean, I'm not taken aback. I mean, it's just as salient for me, but really it's the most common answer to this question by experts. And I'm talking real intense experts across so many fields of science. So it seems to be wherever their work is, whether they're actively working on the project, on this problem because they themselves are ecologists or, biologists or whatever, or whether they work in like a field that's very divorced from this, like a technological field or the like, that this is what is keeping so many people up at night. That those of us who can read the literature, because obviously, sadly, the literature is often a bit hard to approach if you don't have the training in how to read literature. But that those of us who communicate with other experts on a regular basis, and I think a lot of people who don't, but who have a good handle on this, it's hard to ignore how daunting this problem is and how fundamentally important it is. It's amazing to me to this day that there are people who don't even believe it exists, that they don't.
Yeah, that's a whole other thing.
Yeah, it's a whole other thing. That they don't even see it as a problem, or the political will, the whatever, all the different agenda reasons for that. But when you talk to people who really who do understand that this is a problem, it's pretty incredible how many experts across so many different fields are like, this is the one. It's what we've got to prioritize.
Yeah, I mean, you can't ignore the data.
Yeah, exactly. There you go. You said it. So you said what I was trying to get to in like 4 words. I love it. You can't ignore the data. 5 words. You can't ignore the data. So Grace, thank you so much for spending your time with us today. The book, everybody, is Models of the Mind: How Physics, Engineering, and Mathematics Have Shaped Our Understanding of the Brain, by Dr. Grace Lindsay. Thank you so much for your time today. It was really, really informative.
Thank you for having me.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.